Okay. So our agenda for today is transmission gate or TG logic. Second is rise time and fall times, and third is device sizing. So transmission gate logic can be defined in this way. TG logic or transmission gate logic family refers to implementing a logic functionality using transmission gate. Now transmission gate is basically a logic gate or a digital switch. Okay, transmission gate is basically a logic gate or a digital switch which overcomes the drawbacks of both PMOS and NMOS as switches. Okay, so transmission gate is basically a digital switch which overcomes the drawbacks of both PMOS and NMOS as switches. So we already know that the problem with PMOS switch is that PMOS switch, it gives a strong 1 but a weak 0, and NMOS gives a weak 1 and a strong 0. So this drawback of PMOS and this drawback of NMOS is overcome if I use transmission gate as a switch. Now, how is transmission gate able to overcome the individual drawbacks of PMOS switch? Because transmission gate is nothing but a parallel connection between one PMOS and one NMOS as shown below. Okay, so the construction of a transmission gate can be shown like this. So we have one PMOS device here and we have one NMOS device here, and we can show the terminals. Drain, source, gate. Drain, source, and gate. So if I connect the drain of PMOS to drain of NMOS, if I connect source of PMOS to source of NMOS, then what I obtain is actually called as a transmission gate. So transmission gate is a parallel connection between one PMOS and one NMOS. So this end is called as input end, this end is called as output end, and then there is one control signal which is actually named as C, and this control signal is given to the gate of NMOS, and to the gate of PMOS we are going to apply the complement of control signal, right? So basically C is the control signal, not C bar, but because NMOS and PMOS transistor operate with exactly opposite kind of logics at their gate terminal, that is why I have to apply C bar to PMOS gate if I apply C to the NMOS gate. Now naturally we know that this is the control signal, so I purposefully call this as C because this is my control signal. So I need to redraw this diagram because transmission gate consists of one PMOS and one NMOS with control signal C applied to the gate of NMOS and a complement of that control signal applied to a PMOS. That is why this is not the complete diagram. If I want to draw the complete diagram, then I have to draw it like this. So I will draw the PMOS here. PMOS, NMOS, PMOS, NMOS, drain, source, gate, gate, source, drain. Okay, and please note that this is again a CMOS NOT gate. That means what? It is having again one PMOS plus one NMOS. So we can actually say that a transmission gate along with its control logic is equal to 4 MOSFETs. Is it okay? So we can write a comment here. Thus, one transmission gate is equal to 4 MOSFETs. Okay, 2 PMOS and 2 NMOS. Okay, another important point is that the control signal C is the signal which is applied to gate of NMOS. Okay, now let us see how this transmission gate actually operates. So redrawing figure number 2. Case 1, C equal to 0. Okay, so C equal to 0, 1. Okay, PMOS, NMOS. Okay, so in this case what will happen is, if control signal C is 0, then the gate of NMOS will get a 0 and the gate of PMOS will get a 1. And you know that PMOS for gate equal to 1 is in off condition. Similarly, NMOS with gate equal to 0 is also an off condition. So basically, when control signal equal to 0, my system becomes like this. Okay, so output is equal to Z, floating or high impedance. So we conclude that with C equal to 0, the transmission gate is off or it is open. That means there is a disconnection between input and output. Case number 2, C equal to 1. C equal to 1, then closed. Okay, so based on the above two cases, I can conclude that TG becomes on for C equal to 1, or gate of NMOS is light 1. We also say that the NMOS side of TG should get 1, or we also say that the PMOS side of transmission gate gets a 0. Both the things are correct. Okay, now this was about the construction and operation of the MOSFET, and now we go to the symbols. So what are the different symbols which are used for drawing a transmission gate on paper? There are many different symbols which are acceptable. Okay, so the first symbol is this. Okay, C bar. Okay, so this is called as the PMOS side, and this is called as NMOS side. Another symbol is okay. So usually in our implementations we'll be using this one. Other two are a little more complicated, right? So this is the preferred one which can be used. So rather than drawing the detailed MOSFET equivalent structure for a transmission gate, we can actually better use this symbol. Okay, so now we see here that in this case number 2, when control signal equal to 1, both PMOS and NMOS are on. So we can therefore say here that because TG equal to on, because both PMOS and NMOS are simultaneously on, transmission gate gives both strong 1 and strong 0. So we should always understand this thing, that the reason why transmission gate is able to give both a strong 1 and strong 0 is that because both PMOS and NMOS are simultaneously on, the transmission gate gives strong 1 and strong 0. Okay, now we come to how to implement multiplexers using transmission gate. So before we discuss how to implement a multiplexer using transmission gate, I want you to actually calculate what are the number of MOSFETs which will be required if I want to implement 2:1 MUX using CMOS logic. So till we do not first find a transistor count for implementing 2:1 MUX using CMOS logic, we will not be able to appreciate what is the utility of this particular logic family transmission gate, right? So now we will say find the MOSFET count for implementing a 2:1 MUX using CCMOS logic. Okay, so how to find out solution? Okay, so the Boolean expression representing the functionality of a 2:1 MUX is y equal to S bar ANDed with I naught, OR with S ANDed with I1. Okay. Now we also know that a NAND gate needs 4 MOSFETs, NOR needs 4 MOSFETs, AND needs 6 MOSFETs, OR needs 6 MOSFETs, and NOT gate needs 2 MOSFETs, right? So now we know that according to this statistics, we can actually calculate what is the transistor count. It's very simple. NOT gate to convert S to S bar will take 2. Okay. This ANDing will take 6. This ANDing will take 6. And this ORing will take 6. Right. So the transistor count for implementing a 2:1 multiplexer using CCMOS logic is equal to 20. Right. So 20 MOSFETs are required for implementing a tiny puny system 2:1 MUX using CCMOS logic. Now we will see how to implement a multiplexer using TG logic. Then we will compare the number of MOSFETs required for TG logic implementation versus CCMOS logic implementation. Implement a 2:1 MUX using transmission gate logic. So we have our multiplexer here, the ANSI symbol for multiplexer. Okay. For the sake of writing the truth table, we can say input I0, input I1, select line S and output Y. And we know that my truth table now we know from this particular construction that one transmission gate can accept only one input. Okay, so this is what we write here. One transmission gate can accept only one input. MUX 2:1 MUX accepts two inputs. So we need two transmission gates. So we are going to use this particular symbol for constructing multiplexer. So my first transmission gate, second transmission gate. Now whether this side is PMOS side or this side is PMOS side, whether this side is PMOS side or this side is PMOS side, that we will not decide now. Okay, so this is my first transmission gate. and it is going to accept my first input of multiplexer I0. That is why I will give the name TG0. Similarly, my second multiplexer input I1 is applied to the second transmission gate. That is why I will name it as TG1. And what I'm going to do is my output Y of the multiplexer has to be the combination of the outputs of the two transmission gates. That is why the outputs of the transmission gates are wired together. Okay. Now the question comes that I have mapped already. I have mapped I0, I have mapped I1, I have mapped Y also. So out of the four signals associated with multiplexer, I0 is nothing but the input of the first transmission gate, I1 is the input of second transmission gate, and the wired ORing of the outputs of individual transmission gates is my output Y. Now the question comes is, where do I put the select line? So I will have to do some preliminary analysis for this. So my select line is here, and now I go here and I stop, right? So now understand one thing, that when my select line is equal to 0, my truth table says that output should be I0. So when my select line is 0, my I0 should come outside, for which my TG0 should become on and my TG1 should become off. Okay, so I have to decide. So when select line is equal to 0, to make Y is equal to I0, my upper transmission gate should become on and my lower transmission gate should become off. So we know very well that the rule for switching on and off the transmission gate is that NMOS side of transmission gate should get 1 or the PMOS side of transmission gate should get a 0. Okay, so this particular rule that the PMOS side of transmission gate should get a 0 will make the transmission gate on. We use this principle here. So when S is 0, upper transmission gate should become on. That means this 0 should go to the PMOS side of TG0. So when this side gets a 0, automatically we know that the upper side has to be NMOS side. So I have found out that when S equal to 0 is applied to the PMOS side of TG0, only then this TG0 is going to become on and I0 will be sent to the output. So this has to be PMOS side. This will be NMOS side. Okay. Similarly, when TG0 is on, TG1 should be off. So what is the condition for switching off a transmission gate? The condition for switching off a transmission gate is exactly opposite of this thing. That is, if NMOS side receives a 0 and PMOS side receives a 1, then in that case it will become off. So NMOS side should receive a 0 in order to switch off. So naturally, this select line which is equal to 0 must go to the NMOS side of the lower transmission gate. So when this is the NMOS side, naturally this is the PMOS side. Okay. Now let us analyze if our design is correct, right? So what I will do, I will put S equal to 0. So 0, 0. So when this gets 0, this gets 1, this gets 1. So NMOS side of TG0 is equal to 1 and PMOS side of TG0 is equal to 0. So transmission gate 0 becomes on. Other side, the NMOS side of TG1 has got a 0 and PMOS side has got a 1. This becomes a condition for switch off. So TG0 becomes on and we get Y is equal to I0. Now reverse the condition. Okay, reverse the conditions now. Okay, now S is equal to 1. So when S is equal to 1, S is equal to 1, here I have 1, here I have 1, here I have a 0, I have 0, right? So what has happened now is that the NMOS, what has happened now is the PMOS side of TG0 has got a 1 and NMOS side of TG0 has got a 0. So because NMOS side has got a 0, TG0 will be off. Other case, the NMOS side of TG1 has got a 1 and PMOS side has got a 0. So this becomes a condition TG1 equal to on. So what happens is at the output, I now get I1. Okay, so now I get I1. Okay, so our design is correct because for S equal to 0, so we can actually write it like this. Now let us find the transistor count for this implementation. So as we told that one transmission gate, it consumes 4 MOSFETs. Where I have written that? Yeah. So one transmission gate, it takes 4 MOSFETs, right? So this transmission gate will take 4 MOSFETs, not 4 MOSFETs, sorry. TG0, it's a PMOS parallel NMOS, so 2 MOSFETs. TG1 again, 2 MOSFETs, so 2. And there is a complementary relationship between this and this, is it not? So we will need and this NOT gate again CMOS NOT gate, so 2. So conclusion is that it requires six percentage transistor count saving is equal to 28 minus 6 upon 28 into 100. So
Sir, it was 20, no?
yeah, it was 20, correct, it was 20. So how much it will be? 14 upon 20. So, कितना आएगा? 70%.
70%.
70%, yeah. Which is actually very good. Okay, so this is a classic example of how by using transmission gate logic we have actually brought down the MOSFET count of a multiplexer by 70%. Okay, so this was about transmission gate logic, and we will discuss about rise time and fall times now. So rather than just speaking theoretical things, what I will do is that I will open uh, the CMOS inverter in microwind, and I will show you that how rise time and fall time of an inverter is not the same. Okay. Now, one of the expectations from CMOS logic family is that T rise equal to T fall. So actually there are about 14 advantages of using CMOS logic family over bipolar. I will discuss it some other time. So there are basically 14 merits of CMOS logic family over bipolar, and one of them is that CMOS logic family gives equal rise and fall times. You know very well from second year what is rise time and fall time. So basically if we assume that we are applying a clock input to an inverter, if suppose this is my V in and this is my V out, then my clock say goes like this. Okay, so ideally what we should get is when input goes from 0 to 1 and input goes from 1 to 0, at that time my output should also go from 1 to 0 and 0 to 1. But actually what is observed in actually CMOS implementations is this, is that I get something like this. So this is actually VDD, this is actually minus VSS, right? So usually the value of VDD for 90 nanometer technology is actually 1.2 volts. Okay, and what we get is this. Okay, so you know very well that the time taken by any waveform to go from 10% to 90% is rise time. The time taken for the waveform to go from 90% to 10% is actually called as fall time. Okay, so what we basically observe is this. So we make a statement now. If the size of PMOS and that of NMOS is equal, rise time is not equal to fall time. Okay, so the statement is, if the sizes of NMOS and PMOS transistors is equal, then rise time is not equal to fall time. Okay, so now what we see is this: in microwind tool, we have the width of PMOS equal to 500 nanometers, the length of PMOS is equal to 100 nanometers. Okay, similarly we see the width of NMOS is equal to 500 nanometers and length of NMOS equal to 100 nanometers. We also know that the size of any MOSFET is given as W upon L. So here we see that the size of PMOS P equal to WP upon LP equal to 5. Similarly, the size of NMOS N is width of NMOS upon length of NMOS equal to 5. So we see here that the size of PMOS is 5, size of NMOS is also 5. Okay, so we say that the relative sizes of PMOS and NMOS is P upon N equal to 1. Okay, so that is why we say that if the size of PMOS and that of NMOS is equal, or we say that if the relative size of the devices is 1. So if PMOS and NMOS have equal size, or we say the relative size equal to 1, what we get is rise time is not equal to fall time. Now we will go to microwind directly and I will show you. So I hope that my microwind interface is visible to you.
Yes,
Yes?
sir.
Yes, sir. Okay. So this is my CMOS inverter. Now what I'll do is that I will just shoot the uh, capacitive load. So here if we see, I have kept, so when I open the MOS generator, then by default we see if I select PMOS, the width is 500 nano, length is 100 nano. So the size is 5. If I select NMOS transistor, still width is 500 nano, length is 500 nano, size is 500 upon 100 is 5. So whenever I use MOS generator to place PMOS and NMOS in the workspace, it by default offers me PMOS with size 5, NMOS with size 5, and that is why relative size is 1. So when I simulate this, what I get is this. Okay, are you able to see this now? Here my waveform in bottom half V out, which is in red color, is clearly showing that the rise time is 3 picoseconds and fall time is 1 picoseconds. I'll again increase the number of cycles and we see the same effect. You see here. So after a few cycles, I am clearly seeing that my rise time is 3 and fall time is 1. So when I use 90 nanometer technology and I use PMOS with size 5, NMOS with size 5, that means relative size is 1, rise time is not equal to fall time. This is a proof. The tool tells you the practical values. So even multisim is telling me that with PMOS and NMOSs of equal size, that is the relative size is 1, rise time is not equal to what is called as transistor sizing. So we will soon prove in the next session that if my PMOS is made 2.5 times larger compared to NMOS, then I have T rise equal to T fall. So what is the statement? If my size of PMOS is 2.5 times size of NMOS, then I can achieve rise time equal to fall time. And this relativity between the two, it stems from the fact that the mobility of an electron is approximately 2.5 times the mobility of a hole, at least in silicon material. We'll go back to microwind and we will open another layout which has this kind of a relationship. So this is a layout of a CMOS inverter where I have made PMOS 2.5 times larger than NMOS. See the simulation now. Okay. See, it is clear in front of us that the rise time and fall times have now become equal. 5 picoseconds and 5 picoseconds. You see, so it is becoming equal. Which is a proof. So yes, initially the rise time was 3 picoseconds and fall time was 1 picoseconds. So rise time has increased from 3 picoseconds to 5 picoseconds. Fall time has increased from 1 picoseconds to 5 picoseconds. But the fact is the rise time and fall time have become equal. So we have achieved the merit which is expected from a CMOS logic family, that is comparable rise and fall times. Got the point? Now I have one more layout in which I have made both the designs and we can actually see that. So unequal and equal, both layouts are in one file. So we see here uh, the left side layout is having PMOS 2.5 times NMOS. So the output is named as Vout underscore unequal sized. And the right side layout is with P equal to N. Okay. And we have the output named as Vout equal. So I will simulate it and show how we can see the difference. Okay, so what I can switch on the visibility now. So I go here and I will switch off the visibility of the input signals. I will say not visible in simulation, not visible in simulation, and I will check the visibility of Vout unequal and also Vout equal. Yeah, so now I expect that both waveforms should be seen here. Okay. So maybe I will select this thing. Anyways, it is not able to show, but I still showed it to you. Okay. Okay.